The next lesson in our reactions and stoichiometry unit is on the details of displacement reactions. This is simply continuing with the same learning target that was finished on the last video. This is about being able to predict the products of simple chemical reactions. Let's take a look at a more detailed approach to single displacement reactions. Recall that in a single displacement reaction we have a free element. In this case, it's indicated by the letter A, react with a compound. A will then displace or replace one of those two elements that make up the compound, in this case showing it replacing B, and B gets kicked out as a lone element. However, A will only displace B if it is more reactive or more active. Those terms are oftentimes used synonymously in chemistry, than B. So if A is more reactive than B, then the reaction we're showing up here will in fact happen. If it's less reactive or less active than B, it won't. Now the question you probably have is, how would we know if an element is more active or reactive than another? This is when we need to use what's called an activity series. And this is something you would simply look up. Here's an example of an activity series. It simply lists elements, in this case metals for the most part, by their activities or reactivities. So notice at the top here, these are labeled most reactive. So potassium is more reactive than sodium, which is more reactive than calcium, and so on. So if one of the elements from above is the free element, it will replace any element below it, but not vice versa. Okay, so just reading what C says here, a metal will only displace a metal below it on the series. So for example, potassium would be able to displace any of these metals here, whereas platinum would not be able to replace any of them because it's the lowest on the series. Now this is just an activity series that has some common metals. Obviously there are a lot missing, but this gives us a basic idea of what we're talking about whenever we talk about an activity series. Let's take a look at some examples of how we would use this idea of an activity series. Let's suppose we were given these reactants, potassium and copper 2 nitrate, and we're asked to predict the products of the reaction. Well, we can see it's going to be a single displacement, most likely because we have a free element reacting with a compound. The fact that the free element is a metal tells us it will replace the cation in the compound, so it would take the place of the copper, and the copper would get kicked out. Now this will only happen though if potassium is in fact more active than copper. So this is where we want to look at our activity chart or activity series. Notice potassium, being at the top here, is higher on the list than copper is. So potassium will in fact replace copper. And so that's exactly what will happen. So we would write the equation here. Potassium reacting with copper 2 nitrate to give us potassium nitrate and copper. So that will in fact occur. Now what if we reverse the scenario? What if we started with copper and potassium nitrate? So this time copper is the free element. So if this reaction were to occur, the copper would replace the potassium would get kicked out. This would only happen if copper is more active than potassium. Again, going back to our activity series here, copper is less reactive than potassium, so this will not occur. Okay, this reaction will not happen. So what we would write here, if we were given these two reactants and asked to determine what the products would be, we would simply write no reaction, or NR, to mean no reaction, because the copper is less reactive than the potassium. Nothing will occur. Now that we've seen how an activity series applies to these single displacement reactions, I want you to do some practice on your own. I'm going to give you the formula of the reactants in a reaction, and then you will write the product or the products, and then if no reaction will occur, you just write NR and explain why. Here is an activity series. Notice this one's slightly different than the one you just saw. We have metals listed on the left, and then if we have nonmetals, specifically halogens, there's an activity series here that appears on the right. Notice they're listed by decreasing activity. So at the top would be the most active metals and the most active nonmetals, and as we go down, they become less active. So as each one pops up, pause the video, try it yourself, see how you do. First one, we have sodium chloride reacting with bromine. If a reaction is going to occur here, the bromine would replace the chlorine. It's going to replace the nonmetal or the anion, because bromine itself is an anion or a nonmetal. So we need to consult our activity series here. Notice bromine is less active than chlorine. So this will not happen. This would be no reaction because that bromine is less active than chlorine. Example number 2, magnesium oxide reacting with sodium. In this reaction, the sodium would replace the magnesium. The magnesium would get kicked out by itself. So consult our activity series here. Here's sodium. Magnesium is directly below it. So sodium is in fact more active than magnesium. So this reaction will occur. The sodium will replace the magnesium. So we get sodium oxide and we get magnesium. Example C. We have chlorine reacting with rubidium iodide. In this case, the chlorine would replace the iodine. Again, the chlorine's a nonmetal, so it will replace the anion. So look at our activity series here. Chlorine is in fact more active than iodine, so this reaction will occur. Rubidium chloride we get for a product, and then we get the iodine as the lone element product. Last example here, we have tin and chromium 3 sulfate. In this example, the tin would replace the chromium. So if we look at our activity series, here is chromium about halfway through, and then tin is a few down from that. So tin is less active than the chromium, so this would be no reaction. If the tin is going to replace the chromium, it must in fact be more active, but it is not, so no reaction will occur. Alright, so there's some details on single displacement reactions. We're going to look at some details for double displacement reactions as well. Here is our general equation for a double displacement. Recall that we have two ionic compounds and we simply have an ion exchange. So A and C exchange partners as we're showing here, and this would give us AD and CB in this example. However, this reaction will only occur if one of the products, so in this case AD or CB in our general formula, if one of them is insoluble in water. That's the only time this would occur. Now, that seems kind of like a funny stipulation, but there is a very specific reason for why that is. There's the question, why? Well, it goes back to the fact that ionic compounds, they dissociate when they are dissolved. Now, what does that mean? Well, here is an example of what that means. If we take sodium chloride, so that's table salt, and notice I'm indicating it's a solid here, and we put it in water, and it dissolves, what happens is the sodium chloride crystal breaks apart into sodium ions and chloride ions. They simply scatter. Okay, those ions, remember, in an ionic compound, they're packed tightly into a repeating pattern that we call a crystal. That crystal disappears. Disappears isn't a good word. That crystal simply breaks apart, and each ion is separated from all the others. So they're individual ions. Now, why is that important when considering double displacement reactions? Here's another example of an ionic compound dissolving. Notice in this case we have potassium sulfate. We get 2 potassium ions. I can see that in the formula. There are 2 potassium ions, and then I get a sulfate ion which has a 2- charge. So that happens anytime an ionic compound dissolves. It dissociates into its component ions. So let's consider an example of a double displacement reaction and see why this idea of one of the products being insoluble in water is important. Alright, so here's our reaction. We have sodium chloride reacting with lithium nitrate. And notice they're both dissolved. They're both aqueous solutions. We mix them together. Here is what we would predict for the products. Sodium nitrate, so the sodium and the lithium have simply exchanged partners. So the sodium is now in a compound with the nitrate ion. The lithium is now with the chloride ion. Now there's a reason I have them each in a different color here. Notice every single one of these substances, both the reactants and the products, they're all aqueous. They're all soluble in water. So what actually is existing here, and this is why the different colors help us, the sodium chloride, even though we might write it like this, actually exists as a separate sodium ion and chloride ions. That's how it exists when it's in solution. Likewise, lithium nitrate, because it's dissolved in water, exists as separate ions, lithium ions and nitrate ions. Look at our products. Also aqueous, they're soluble in water. So the sodium nitrate exists as sodium ions and nitrate ions. Same thing with the lithium chloride. It exists as lithium ion and chloride ions. Now if we compare our reactants and our products, we will notice there's absolutely nothing different about this. I have sodium ions on each side. I have chloride ions on each side. I have lithium ions on each side. I have nitrate ions on each side. No reaction occurred. Okay? It might look like it whenever we write the formulas like we do here, when we're not showing what actually exists, but there are no new products formed. When we mix sodium chloride and lithium nitrate, nothing happens. These ions already exist just like this. We mix them together, they still exist in the same manner. No reaction occurred. So this is why we have to have at least one product that is insoluble, meaning it does not dissolve in water. So if we were to be given this reaction, the answer would be NR, no reaction, nothing occurs. Here's a picture to help you understand what we mean by dissociation. Here on the left side we have a sodium chloride crystal. So picture this, you've just put some salt in water. Maybe you're going to make some spaghetti, so you're adding some salt to your pot of water. And this is before it dissolves. Notice we have a crystal of sodium chloride. The sodium ions would be the purple ions there with the plus sign. The chloride ions would be the green ones here with the minus sign. So this is how it exists as a solid. You put it in water, it dissolves, and what that means is these ions get pulled off of the crystal. Notice here is a sodium ion, here's a chloride ion, here's another chloride ion, here's a sodium ion, here's a chloride, here's a sodium. And we say that these ions are hydrated. And the reason why that is they get surrounded by the water molecules. Notice in each of these ions that are being shown, every one of them is surrounded by water molecules. That's what happens whenever any ionic compound dissolves. That's why in the previous slide there, I showed you how those ions actually exist. Alright, so let's take a look at some examples of how we go about using this idea of solubility. A question you might have is, how do I know whether or not one of these products is soluble or not? Well, there really is no way of knowing unless you either A, do the experiment yourself, do the reaction, and see what happens, or B, looking it up on a solubility chart, or what's called a solubility rules. So notice how this is organized. At the top here, we are told soluble ionic compounds. So if the ionic compound contains any of these ions, and notice these rules are based on anions, so nitrate, acetate, chloride, bromide, iodide, sulfate, they would be soluble. In other words, they do dissolve in water. However, it lists important exceptions. Notice for nitrate and acetates, there really aren't any exceptions that are listed here. In fact, nitrates and acetates, they're virtually all soluble. They dissolve in water. However, chlorides, while they generally are soluble, if it is silver chloride, notice silver is listed here, if it is mercury chloride, if it is lead 2 chloride, then it would not be soluble. That would be an exception. So that's how we would read those rules. On the bottom, we have the opposite. We're listing insoluble ionic compounds. So ionic compounds that contain sulfide ion, carbonates, phosphates, hydroxides, they are insoluble with the exceptions that are listed here. So let's use this idea to figure out how we go about using this for double displacement reactions. Alright, some examples. First one, here's the reaction. We're given lead 2 nitrate and sodium iodide. The first thing you're going to want to do is identify the possible product. So think about how the double displacement reaction will work. The lead and the sodium will exchange partners. So the lead will be in a compound with the iodide, the sodium will be in a compound with the nitrate. So identifying our possible products, that would be lead 2 iodide. Okay, remember the charges on the ions don't change. The lead's 2 plus here, so it'll still be 2 plus with the iodide, so PbI2, and then NaNO3, the sodium nitrate. So those are our possible products. Now what you want to do is consult the solubility rules. So you want to look up these two compounds on our solubility rules over here and determine if they're soluble or not in water. So the lead 2 iodide, that's an iodide. So here the iodides are listed under soluble ionic compounds. However, notice the lead 2 ion is an exception. So if it's lead 2 iodide, like we have here, that would be insoluble in water. PbI2 is insoluble. I do the same thing for the sodium nitrate. Nitrates are also listed up here as soluble compounds. There are no exceptions. So sodium nitrate is in fact soluble. So what this tells us is a precipitation reaction will occur. The PbI2 will not be dissolved in water. It is not soluble. So it will precipitate out as a solid. So here would be our equation. We have our reactants, the lead 2 nitrate and the sodium iodide. And then we have lead 2 iodide. Notice it's marked as a solid because it is not soluble in water. And then we have sodium nitrate. In other words, what we're saying here is this PbI2, because it's a solid, it will not exist as individual ions. It will not be dissociated. It will form a crystal of lead 2 and iodide ions. That's why we write it as such. If we wanted to show the ions that are present, we would separate these because the lead 2 nitrate is dissolved in water. We would separate these because the sodium iodide is dissolved in water. And we would separate these because the sodium nitrate is dissolved in water. Here we have barium acetate reacting with sodium sulfide. So again, we want to identify our possible products. Just flip your cation partners. So the barium would go with the sulfide ion, that would be BAS. The sodium would go with the acetate, so that would be NaCH3COO. Now we want to consult our solubility rules. So the first one we have is barium sulfide. Notice sulfides are listed as being insoluble. However, important exceptions here. Notice the barium ion is listed as an exception, so that makes the barium sulfide soluble. Likewise, sodium acetate is also soluble because acetates are listed up here under soluble compounds. There are no exceptions listed, so sodium acetate is also soluble. So what that means here is no reaction will occur. Both of those products, if we can even call them products, are soluble in water. So what we would have here, the barium acetate plus the sodium sulfide gives us no reaction. Next example, we have hydrochloric acid, HCl, reacting with barium hydroxide, which is a base, and then we want to come up with the products. So first thing we want to do is identify our possible products. So this would give us H2O, water. You might be wondering how we get water from this. Notice the cation from the hydrochloric acid is hydrogen. The anion from the barium hydroxide is hydroxide. So that would be a hydrogen with a hydroxide. Well, that's H2O. That's water. The other possible product would be barium chloride. So now we need to figure out the solubilities. Water, okay, H2O. You notice it's not listed over here. You might think, well, is water soluble? Well, water isn't soluble or insoluble in water. It just joins with the rest of the water molecules. In other words, this H2O that gets formed will just become part of the solvent that's already there. Notice these two things are both dissolved in water already. So when we mix hydrochloric acid and barium hydroxide, one of the products will simply be more water molecules that will just mix in with the rest of the solution. Notice now also that barium chloride listed here under these soluble compounds. Barium is not an exception, so the barium chloride is soluble. So the result here will be a water-forming reaction. We won't get a precipitate. We're not going to get a solid out of this. Here would be the equation. We have the hydrochloric acid mixing with the barium hydroxide. Here is our water as a product. Notice it's written as a liquid. We don't write AQ because water doesn't dissolve in water. It just becomes another water molecule, mixes in with the rest of them. And then we would have the aqueous barium chloride still present. One more example. We have hydrogen sulfate, or better known as sulfuric acid, reacting with ammonium carbonate. Again, we want to identify our possible products. You might think one of the possible products is H2CO3. That would be the hydrogen ion combining with the carbonate ion. However, whenever hydrogen carbonate, or also known as carbonic acid, Whenever it is formed and we're in solution, as we are here, notice both of these are dissolved in water, that immediately breaks apart and gives you water and carbon dioxide. Immediately. This H2CO3 really does not exist at all. The other possible product would be the ammonium sulfate, the ammonium ion combining with the sulfate ion as we see here. So we want to look at our solubility rules. Well, for that first one, we actually get two products. We get water, and as we just talked about in the last example, that will just become part of the solvent. The carbon dioxide, that's a gas. So that's where you're going to get bubbles. In fact, if you're familiar at all with mixing vinegar and baking soda, the reason you get bubbles, that's carbon dioxide gas being produced there. The ammonium sulfate, that is soluble. Notice sulfates are listed as soluble compounds. Ammonium is not listed as an example to that, or excuse me, as an exception to that. So the ammonium sulfate is in fact soluble. The result here will be a gas-forming reaction. So our equation here, we have the sulfuric acid reacting with the ammonium carbonate. We get water. Again, notice the state there, it's a liquid, not aqueous. We get carbon dioxide gas, and then we get our aqueous ammonium sulfate. Alright, several examples you've seen there. Give you a chance to practice it now. Just like on the last practice slide, I'll give you the equation for the reactants. You need to figure out what the products are going to be. If no reaction will occur, write NR, explain why. And again, notice here are your solubility rules to consult. First one, we have sodium hydroxide and lithium nitrate. This is going to be no reaction because both of the products that we might anticipate are soluble. Okay, we would predict sodium nitrate. Notice nitrates are soluble, there's no exceptions. We would expect lithium hydroxide. Okay, hydroxide is listed as an ionic compound that's insoluble. However, notice one of the exceptions are alkali metal cations. Well, lithium is an alkali metal, so the alkali metal cation with hydroxide makes it soluble. So this would be no reaction. Next practice, rubidium hydroxide with phosphoric acid. Here your products would be rubidium phosphate, which is in fact soluble. Phosphates are generally insoluble, however, just like in the last problem there, alkali metal cations is listed as an exception, so that would be aqueous. The reason this reaction does occur is because of the water that gets formed. Okay, notice we have a hydrogen ion combining with a hydroxide, so this is another example of one of those water-forming reactions. Next one, we have copper 2 chloride and sodium phosphate. This will give us a precipitation reaction. One of the products is insoluble. That's the copper 2 phosphate. Notice phosphates are listed as insoluble, and then the copper 2 ion is not listed as an exception. So that will not be dissolved in water. That will precipitate out as a solid. And then we have the sodium chloride, which is soluble. We're very familiar with that. Chlorides are listed as being ionic compounds that are in fact soluble. The sodium is not an exception to that. One more practice. We have potassium hydrogen carbonate and hydrogen bromide or hydrobromic acid. This will be a gas-forming reaction. I know this because I have an acid, the hydrogen bromide or the hydrobromic acid, combining with a carbonate, or in this case it's a bicarbonate, that's HCO3. So we would expect the H2CO3 to be formed. But remember, whenever we get that immediately breaks apart into what we see here. We have water and carbon dioxide gas, so we get a gas-forming reaction. And then our other product would be the potassium with the bromide ion. That would give us potassium bromide, which is in fact soluble. Alright, lots of examples here, lots of additional details on the displacement reactions and how we determine what the products will be and whether or not a reaction will even occur. So this completes our 6th learning target. We now are able to predict the products of simple chemical reactions.